Welcome to the AI Research Roundup. I'm Alex. Today, we are looking at a paper trending on X, published on August 18th, 2025, just 2 days ago. The standout result is simple but powerful. A higher signal-to-noise ratio in a benchmark strongly predicts better small to large decision accuracy, with correlation around 0.79, and it also tracks scaling law prediction error. The paper is titled, Signal and Noise, a Framework for Reducing Uncertainty in Language Model Evaluation. And as we will see later, the implications for practical model selection are quite significant. Beyond that, the study shows metric choice, checkpoint averaging, and subtask filtering reliably boost benchmark usefulness. Building on that, the tweets highlight signal and noise as simple metrics to tell real improvements from randomness, and they ask whether benchmarks detect true performance differences, with moderate engagement around 70 likes. Alright, this figure compares 3 benchmarks across compute, each line showing a different pre-training corpus, with stars marking final checkpoints. The left panel shows low signal and low noise, where curves cluster tightly so rankings blur. The middle panel shows high signal but high noise, with widespread yet jittery insets. The right panel shows the sweet spot, low noise and high signal, where small model orderings track to larger ones. The insets visualize within run variability for the 1 billion model. Next, a 3-panel figure ties everything together. The left scatter plots decision accuracy against relative dispersion, showing weak correlation. The middle scatter compares decision accuracy to relative standard deviation of final checkpoints, again weak. The right scatter uses signal-to-noise ratio on the x-axis, and a clear upward trend appears with a gray fit band. Larger dots indicate bigger models, but the pattern holds across sizes. The takeaway is straightforward. Higher signal-to-noise ratio predicts better decision accuracy across benchmarks. Continuing the thread, the left scatter links target noise to scaling law error. As the relative standard deviation of final checkpoints rises, the prediction error also increases, roughly following a downward-sloped trend line in log space. Now, shifting right, the social IQA panel shows the scaling curve across compute, with the light blue fit predicting the 13 billion model. The inset highlights the target's checkpoint wiggle, labeled noise, and the resulting 2.4% error, illustrating how target variability bounds achievable prediction accuracy. Now we see the subset selection intervention in action. The 6 panels compare sorting subtasks by signal-to-noise ratio versus a random order. Focus on the full grid first, then notice how, for MMLU, the left panel shows signal-to-noise ratio peaking around the top 16 subtasks, and the middle panel shows decision accuracy improving accordingly. The right panel shows lower relative standard deviation at the scaling target. The bottom row repeats this for AutoBencher, where the best subset is about 6 subtasks, yielding better accuracy and lower target noise. Okay, this table summarizes the checkpoint averaging intervention. The left block reports decision accuracy from small to 1 billion models, comparing a single final checkpoint against averaging small models, averaging targets, or averaging both. You can scan the boldface numbers to see consistent gains, and the all 30 task average rises by about 2.4 percentage points when averaging both. Moving to the right block, the prediction error for 13 billion targets drops when training checkpoints are averaged, with the all 30 task average falling from 1.03 to 0.86. Building on that, 2 takeaways stand out. Prioritize high signal-to-noise ratio benchmarks, since they better preserve model rankings and reduce scaling law errors, and apply simple fixes like checkpoint averaging, metric choice like bits per byte, and subtask filtering. Signal means spread across models, noise means training variability. That is it for the AI Research Roundup. I am Alex. Thanks for listening.